Welcome to the Flip Notes Studying the Sun, Part 1. We touched upon this in class already, so a lot of this is review, but it's good to know. Good to have since I'm not there with you. Let's see. If you have not signed up for Remind, which I think all of you have, I'm pretty sure, go ahead and just make sure you're signed up. Again, it's texting 81010, message at MR Denner. And you get my reminds. That's how I'm going to keep in contact with you for at least the next 2 weeks or so until we're back together again in school. Again, remember the first people to observe sunspots were the Chinese over 1,500 years ago, with our records indicate anyway, without a telescope. So yeah, they stared at it blindly with just naked eyes, and yeah, it became blind because they burned their retina. They stared long enough to see those spots and verify it with each other. It's crazy. Galileo Galilei, speaking about being crazy, remember the first man on record to have used a telescope to point at the stars for astronomy rather than just looking across the ocean, also decided to find a lot of stuff. He found the big moons that orbit Jupiter. He also found sunspots, and he stared at it long enough to realize the sun rotates. Boy, to see the spots moving across the sun that long, you know he burned his retina. Yeah, he went blind. That's a fact. 1859, the spectra of the sun using spectroscopy as we use it in chemistry, we found this gas called helium. We named it helium because we saw it on the Helios on the sun before we saw it here on Earth. Okay, the solar telescope, we talked about this as well. Because it's not good to stare straight at the sun, you can get one of these things which puts the image of the sun's photosphere onto a white piece of paper so you can look at the sunspots. So a solar telescope is nice. I actually have in my classroom a big old round solar filter, which I put on the end of my telescope, and it looks like a big round mirror, but we can use that to stare straight at the sun with our naked eyes with that between us, and we can see the sunspots, and it's a it's really nice. Otherwise, it just looks like a mirror because it's so dark. Okay, at the telescope at Kitt Peak National Observatory, they they take a huge area of the sun and cast it down that long tube there to the floor. And on that floor, the solar physicists can look at the sun and take precise measurements of the spots and everything. So these are solar physicists, remember, guys who study the sun. Specific names of the astronomers who study the sun are called solar physicists. Yeah, these 6 guys are really solar physicists. Again, Skylab missions back when I was little, they were huge because they photographed the sun and sent us cool pictures. They were the big ones because they did a lot of the labs up there too. And kind of like you guys have your little science news now, we had that back then too. From 1962 to 1989, again, many satellites were used to view the sun outside of our atmosphere because our atmosphere does protect us from a lot of the sun's harmful radiation. So in 1990, we sent up a satellite which didn't just see the equator of the sun, which we orbit around, but it went north to south and saw the poles. Since it went north to south, we named it Ulysses, kind of like Ulysses S. Grant. Remember back when the North and the South fought? It found some good stuff, took a lot of pictures. The SOHO, the Solar and Heliospheric Observatory, SOHO is a lot easier to say, was an international collaboration between European Space Agency and NASA. And they launched that back in 95. They've discovered a lot of stuff since then. It's nice because we see that the sun really affects our global climate a lot more than does our carbon footprint, even though it's not good for us to pollute as much as we do. The sun plays a huge role. If you look back in the older science books and the old astronomy books, they show you that global warming and global climate has changed dramatically on cycles. So, and the sun has a lot to do with that. Now, properties of the sun. You can see that nice picture. I love this. It shows Jupiter, our biggest planet in our solar system, which could take all the other planets combined and crush into Jupiter. Jupiter is but a mere dot on the sun's surface. The sun is 110 Earths wide. You string 110 Earths side to side, and you can make the diameter of the sun. But if the sun were a hollow gumball machine and the Earth were gumballs, it'd take over 1,000,000 gumballs of Earth to fit inside the sun. That's a lot. The mass would be taking Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Throw Pluto in. That's fine. Crush them all up 745 times all of that just to make the sun. And the sun is mostly hydrogen and helium. That's a lot of gas. But because it's so massive, the gravity is enough at the core where it can fuse helium. Jupiter is mostly hydrogen, but its gravity is not enough to make it a star. So therefore, it's just a big gas planet. So the surface, what we call the surface, is the photosphere we see. That's the bright yellow part. It is between 5,500 and 6,000 Celsius. Oh, don't you mean Kelvin? Let's see, take 273 from that, you're still in the ballpark. So yeah, between 5,000 and 6,000 Kelvin or 5,000 6,000 Celsius. At that temperature, that 273 doesn't matter a whole hill of beans. It's hot. The interior temperature of the sun at the core is thought to be 15 million Kelvin? Yeah, Kelvin, Celsius. Really, the 273 is irrelevant when you're talking about millions. That's hot. So the sun has really 7 regions we're going to talk about. This says 3 atmospheric regions. Those are on the outside. That's the photosphere, the corona, the chromosphere, and the corona. But really, there's 7 regions of the sun you got to know about. You got to know. So the part we see is called the photosphere. It's bright yellow. Okay, it's about 400 to 500 kilometers thick if you're measuring. So here it shows the sun has the core at 15 million degrees Celsius. Then it radiates out from the core, and then it convects by gases up to the photosphere. And it shows prominences here. So the photosphere of the sun, if you look closely, has these granules. They look like granules of rising, hotter gases, which are the brighter yellow, and the cooler orange gases, which almost look brown. But those are just rising and falling gases. But they're huge. Each little granule is the size of our moon, basically. That's huge. And again, their colors are different because of the falling gases and the rising hotter gases. Kind of like a pot of boiling water. You see bubbles coming up, the hotter stuff comes up and cooler stuff drops. So the sun's atmospheric layer, the outer side, the cooler red chromosphere, has to be photographed using ultraviolet and X-ray telescopes because a light microscope, telescope rather, all it sees is yellow, the brighter, hotter yellow photosphere. The chromosphere is a little bit cooler, and it's red because of all the hydrogen. Oh, here we go. It's red due to the glowing hydrogen. The crown, the corona, not to be confused with the coronavirus, again named after the crown, is very thin, very, very, very tenuous, but it extends over 1,000,000 kilometers away from the sun. It's this huge crown. You can see it at a total eclipse, or in a solar telescope lab, they can put a fake disk over the incoming photosphere, and then they can see the corona. Cool thing about that is you got hydrogen doing some crazy stuff out there, and therefore it gets over 1,000,000 Kelvin, like a 1 to 3 million degrees hot out in that corona. And because of that, it shoots out a lot of stuff called solar winds. We'll talk about that later, a lot of radiation. So you can only see it during a solar eclipse. Like I said, it's very faint, it's very thin, but it gets hot. Okay, now under the photosphere, we have the convection zone. That's where the granules are formed, the rising and cooling gases. Below the convection zone, we have the radiation zone. which radiates heat. It's so hot, it just comes up as radiation. It's not even a gas yet. It's so stinking hot. So the nuclear fusion occurs in the core and takes 4 hydrogen protons, and under the great pressure, they get fused into making a helium, and then neutrinos are shot off, positrons, and energy is shot off. Energy, yeah, photons, light. So the neutrinos, we're going to talk about a little bit later, they're very thin, and we can't really detect them on the Earth's surface because of all the other cosmic radiation. We have to go way deep down the Earth's surface where the other cosmic radiation is blocked, where neutrinos will penetrate right through the Earth. They're so tiny and so fast. And we set up tanks there, and as they change the hydrogen and make it radioactive, we can detect those little blips of light. Problem is, we're not that accurate. Here's the 7 main zones known. I'll put it all together. Ignore the transition zone because I'm not going to talk about that. The very middle, the core, where all the fusion takes place. Hydrogen getting pressed so tightly together to form helium. And that is what, 15 million degrees? That's hot. That's Celsius. And then the radiation zone, where it's still hot, it's radiating upwards until it gets to the convection zone. Convection zone, now it's just hot radiation, hot gases. And that reaches the photosphere, which is our yellow part we see with our eye. And outside the photosphere is the chromosphere. Chromo means color, it's reddish. And then outside the chromosphere, we have the corona, which extends way out there and it gets really hot. And outside the corona, then, the corona causes these solar winds, and I put them on a zone you need to know because the solar winds are very important. They extend clear out past Pluto. They do wreak havoc with our Earth. And, well, our Earth is protected, thank goodness, by the magnetosphere, but they do wreak havoc with astronauts out there because they carry a lot of radiation that's not healthy or safe for astronauts. Solar neutrinos, again, from the sun's core pass through the Earth and can only be detected by underground detectors. And all this basically to say we need these things under Earth and we account them as best as we can. All right, this nice little cutaway view is just for you again to show that you start from the core, go out to the radiation zone, out to the convection zone, out to the photosphere, out to the chromosphere, out to the corona, and then solar winds. So it's just a nice little cutaway to study and know these areas, layers of the sun. Solar prominences are huge. When you get a blast of gases shooting up, a bunch of that gas comes up and it arcs, and it can take a few hours before it comes back down, disappears. And you can put an Earth or two or a few underneath those prominences. They're huge. So they're flame-like arches extending from the photosphere. They last several hours, they can, and they extend millions of kilometers above the photosphere. Here's one that was taken back by SOHO. Let's see, huge prominence blast away, yeah, 10 years ago. From SOHO took this picture. A blast like that, when aimed at Earth, sends so much radiation that back in the 90s, a blast like that was aimed at Earth and it came up upon our North Pole and it pushed the magnetosphere so far down, it penetrated enough to cause a lot of power outages in Canada. Yeah, so it can wreak havoc with us. Sunspots, again, are dark spots on the photosphere. They're larger than the Earth. Here's a couple big ones right here, which will show us the dark inner area we call the umbra, like an umbrella, kind of like in the eclipse. The dark part's the umbra, the lighter part's the penumbra. They're darker because they're cooler than the photosphere. However, they're still about 3,000 Celsius. They're still hot. 3,000 to 4,000 Kelvin. Still stinking hot. The dark spot is called the umbra, and the lighter rim is called the penumbra. So remember that. The penumbra and umbra, very important to know. Sunspots do occur in magnetic pairs, and you can see a north and south magnetic pair. They look a lot like the filings on the end of that magnet right there. And the sun rotation is not the same since it's not a gas. You'll wait to part 2 to find out where it rotates faster.